Today we start with thermodynamics, and this will be the first video of the physics series. Let's start with the zeroth law. The zeroth law of thermodynamics is a very simple law, simple to understand and simple to apply. This is the statement of the zeroth law. If two thermodynamic systems are in thermal equilibrium with a third thermodynamic system, then the first two systems must be in thermal equilibrium with each other. It's essentially like A is equal to B is equal to C. It's really simple to understand by logic that if two systems are in equilibrium with another system, then all of them must be in equilibrium as well. And by thermal equilibrium, we mean two bodies or two systems being in the same temperature. And let's move on to the first law of thermodynamics, which is a much more comprehensive and much more applied law. This is the statement of the first law that energy can neither be created nor destroyed. It can only be converted from one state to another. This first law is essentially another form of the conservation of energy, another form of the law of conservation of energy. And this is essentially the law of conservation of energy being applied to fluids and liquids and other thermodynamic systems. So this is the expression of the first law that work is proportional to heat applied. And basically, the work done will be proportional to the heat applied, or the heat produced will be proportional to the work done. And this formula, this equation, is the central formula of thermodynamics of the first law. The dq is equal to du plus dw. dq means the change of heat, du means the change of internal energy, and dw means the change of work. So remember this formula. This is a very important formula and it will be applied almost everywhere. dq is equal to du plus dw. Now, plus or minus. Plus or minus the in the equation that we just mentioned, dq is equal to du plus dw, all three of the parts of the equation can be either positive or negative. So for dq to be positive, dq to be positive means, let's change the color. So for dq to be positive, if heat is absorbed by the system, that is, if the system is endothermic, okay, if the system is endothermic, dq will be positive. And if the system is exothermic, that is, heat is released from the system, then dq will be negative. Okay, so dq is positive in endothermic systems and dq is negative in exothermic systems. That means if heat is absorbed by the system, dq will be positive, and if heat is released or rejected by the system, then dq will be negative. Okay, now what about du, internal energy? Change of internal energy will be positive if internal energy is increased. Okay, so in the reaction or in the process, if u means internal energy, is increased, if u is increased, then du will be positive. And if du is decreased, if u is decreased, that is, if internal energy is decreased, if u is decreased, then du will be negative. So if internal energy is increased in the process, the change of heat internal energy or du will be positive. And so if it's written that change of energy is 5 kilojoule, you'll be writing it as plus 5 kilojoule. And if it is written as, and if internal energy is decreased in the process, then d will be negative. So you'll be writing it as minus 5 kilojoule. And dw, so change of work, it will be positive when the work is done by the system. Okay, the work is done by the system basically means if if a person is pushing the block or a car is accelerating, okay, then the work is done by the system. Okay, so if work is done by the system, okay, the change of work will be positive. And if work is done on the system, so say a block pushing a person, okay, if work, or what we used to call negative work, so if work is done on the system, then du, or the change of work, will be negative. I hope that's clear. Now let's move on to the processes. Okay, so the first law of thermodynamics governs four individual processes. Okay? They are the isothermal process, adiabatic, isobaric, and isochoric. Let's start with the isothermal process. The isothermal process means isothermal process. Okay, so the isothermal process means same temperature. Okay, iso means same and thermal means temperature. So isothermal process means the same temperature. So del T, or the change of temperature, will be zero. So when del T is zero, that means temperature is constant. Okay, constant temperature. So in isothermal process, the temperature is always constant. Now remember, one thing I forgot to mention is that the internal energy. What do we mean by internal energy? Internal energy is essentially the sum of all the energies in a system. So say kinetic energy, potential energy, mechanical energy, which means the sum of kinetic and potential. So the total mechanical energy of a system is its internal energy. And this internal energy depends on temperature. Now why? Because as you remember from chemistry, the increase of heat increases the vibration within a matter. Okay, vibration of the atoms or man molecules within a matter. So the increase of this vibration leads to an increase of temperature. Sorry, an increase of the total energy, internal energy in the body. So what caused this increase in total energy or increase in vibration? The root cause was the increase of temperature. So, or the application of heat, which increases the temperature. So the in the isothermal process, the formula dq equal to du plus dw changes. Since temperature is constant, the change of internal energy, or du, will also be constant. So dq is equal to, du is constant means it will be zero. Okay, we're not talking about internal energy, we're talking about the change. So constant means no change. So dq is equal to du plus dw, which basically means dq is equal to dw. So in isothermal process, the change of heat and the change of work will be the same. So we can use these formulas of work as the formulas of heat. Okay, we can write this and this. So these are the formulas. W is equal to nRT ln V2 over V1. Now N means number of moles. Number of moles. R means the ideal gas constant, and the only value we'll be using here is 8.314 kilojoule per mole. Sorry, now it's mole. So joule per mole per Kelvin. Okay. 8.314 joule per mole per Kelvin. And that is the only value we'll be using in here. That's the only value that's used in physics. The other values are used in chemistry. So nRT, ln T means temperature, ln V2 over V1. V2 is the final temperature. V2, V2 is the final volume, and V1 is the initial volume. And this, another form of this formula is W is equal to nRT ln P1 over P2, where P1 is the initial pressure. Okay, initial pressure, and P2 is the final pressure. Now, from chemistry, we remember that PV is equal to nRT. Now, this nRT and this nRT and this nRT, they're the same thing. So if we want, we can write W is equal to PV ln V2 over V1, or we could write W is equal to PV ln P1 over P2. Right. Now let's move on to the next process, which is called the adiabatic process. Now, in adiabatic process, okay, so adiabatic process, again, in adiabatic process, the change of heat is 0. So dq or delta Q is equal to 0. That means heat is constant. Heat is constant. There is no change of heat. What happens to our main formula in the adiabatic process? Since dq is 0, so we have 0 is equal to du plus dw. Right? We can write that as du is equal to minus dw, or vice versa. Now, these are the formula of W. Now remember, the formula of this work, it cannot be used as the formula of heat like isothermal. Okay, this is not possible. The formula for work is the same as the formula of heat only in the isothermal process. In adiabatic process, there is no change of heat, so we do not calculate heat here. Actually, we do, but with different formulas. The formula for work is only for work. This is the formula. W is equal to nr over gamma minus 1 into T1 minus T2. Now, T1 and T2. T1 is the initial temperature. And T2 is the final temperature. Remember, do not write del T here, okay? This is not equal to del T, because del T means T2 minus T1. That's not what we want here. We want T1 minus T2. That's why we write it like this, not del T. T1 is the initial temperature and T2 is the final temperature. Another formula, to derive this formula, we use the formula from chemistry, the ideal gas formula, PV is equal to nRT. Okay. Now, as you can see, nR, and if we remove the brackets, then nRT1 and nRT1 and nRT2. From that, we have P1V1 and minus P2 V2 over gamma minus 1. It's the same formula, but just written differently with different values. That's adiabatic. Now, there are some things In the questions, the teachers may not mention that this process is adiabatic process. Your question may not mention how do you understand what process it is. There are some words to understand it. Adiabatic process is sudden, okay? So if the question says a sudden thermodynamic process or a sudden change, then understand that they are mentioning the adiabatic process. If it says very fast, okay, or fast, or insulated, there is no change of heat, so that means the process or the system has to be insulated. So an insulated system means it's an adiabatic process. Or entropy is constant, okay? We'll explain entropy in a separate video. Entropy is constant, or del S, which is a symbol of entropy, or del entropy, change of entropy, is equal to 0. With these words or phrases, you can understand that the question is mentioning an adiabatic process. Let's go back to the isothermal process for a little. For the isothermal process, we can understand it by the word slow. Okay? The isothermal process is a slow process. So a slow process, a slow change, okay? That means it is an isothermal process. Or if it mentions that the temperature is constant or there is no change of temperature, then understand that is the isothermal process. So we're done with adiabatic. Now, there are actually a lot more things to the adiabatic process, but we'll explain that later. Now let's move on to the isobaric process. The isobaric process is really simple. It just means that uh, the change of pressure. Iso means same, and bar, bar, remember the unit of pressure is bar. So isobaric process means the same. Iso means same, and baric means pressure, so same pressure. That means the del change of pressure is equal to 0. So constant pressure, constant pressure. And the work done in isobaric process is W is equal to P, which means pressure. Note that this does not mean change of pressure, it just means the pressure that is there. So there will be only one pressure, not P1 and P2, just P. So say the pressure is given at 5 Pascal or 5 uh, bar. So that's the value we'll use here, 5 bar. There will be no change. P dV. dV means the change of volume. Okay. So V2 minus V1, change of volume, V2 minus V1, W is equal to P dV. And that's it for the isobaric process. It's really simple. And the isochoric process is also very simple. And iso means again same, and choric means volume. So isochoric means the same volume. So there will be no change of volume. Del V or dV is equal to 0. Constant volume. Now can you guess what will be the work in isochoric process? From knowing that the volume is constant, guess what the work will be? Remember in isobaric process we had W is equal to P dV. We have the same formula in isochoric process. So W is equal to P dV. And in isochoric process we know that dV is equal to 0. So that means P into 0 is equal to equal to 0. So work in isochoric process is 0. There is no work done in the isochoric process. Now let's go back to the adiabatic process. Like I said, there are more things in this process. And the factors of equilibrium. From the Le Chatelier's principle, we know the factors of equilibrium are the pressure, volume, and temperature. Or the mole. We don't mention mole here. We can work with volume. It's easier to work with volume. So we have P1. These are three formulas. Okay, the three formulas. The three formulae. So P1, V1, to the power gamma is equal to P2 V2 to the power gamma. This is the relationship between pressure and volume. Then we have T1 V1 to the power gamma minus 1 is equal to T2 V2 to the power gamma minus 1. This is the relationship between temperature and volume. Next we have T1 P1 to the power 1 minus gamma over gamma is equal to T2 P2 to the power 1 minus gamma over gamma. This is the relationship between temperature and pressure. We have to use this formula to find out either P or V or pressure, volume, or temperature in adiabatic process. Now let's go to the explanation of gamma. What is gamma? Gamma is the specific heat ratio of gas. Okay, this is the specific heat ratio of gas. To find gamma, we divide Cp over Cv. And what is Cp? Cp is the specific heat of gas in constant pressure. The specific heat of gas in isobaric process is Cp. And the specific heat, oh sorry, the specific heat of gas, the specific heat of gas in constant volume or isochoric process is Cv. Okay. Cp is the specific heat of gas in isobaric process, and Cv is the specific heat of gas in constant volume in isochoric process. Now we also have the formula for finding Cv and Cp. In the questions, usually gamma is given. If gamma is not given, Cp or Cv is given. Okay, so either two of these three things will be given. Now, in case gamma is not given, and in case gamma is given and you are asked to find Cp or Cv, these are the formula you can use. Cv is equal to R, again R is 8.314 joule per mole per Kelvin, the specific heat, the ideal gas pressure, ideal gas constant over gamma minus 1. Cv is equal to R over gamma minus 1, and Cp is equal to R gamma over gamma minus 1. Okay, and we have this formula for relating Cv and Cp to du and dq respectively. So du is equal to N, again N is the number of moles, N Cv dt. dt is the change of temperature, so T2 minus T1. And dq is equal to N Cp dt. So again, N is the number of moles, Cp is the specific heat of gas in isobaric process, and dt is the change of temperature, T2 minus T1. Now, we have some constant values of gamma that we know. Gamma for polyatomic gases. Polyatomic means any number of atoms above 2. So usually it's triatomic. Okay. Usually triatomic gases, that is gases that have 3 atoms, have the value of 1.67. Sorry, 1.33. 1.33. Okay. So examples of polyatomic or triatomic gases include, say, carbon dioxide, uh, and methane, etc. Okay. So usually triatomic atoms, gases having 3 atoms, or sometimes polyatomic gases having more than 3 atoms, have this value of 1.33. In the question, usually gamma is mentioned. If gamma is not mentioned, they will mention, say, the gas is triatomic or diatomic or monatomic, or they will give you the formula of the gas. So like this formula, and you can guess, you can know factually what the value of gamma will be. Now, gamma for diatomic gases means gases having 2 atoms is 1.41. 1.41. So say gases like oxygen, hydrogen, nitrogen, etc. These gases all have 2 atoms, so they're diatomic, and the value of gamma for them will be 1.41. And gamma for monoatomic, meaning gases having only 1 atom, is 1.33. Now, which gases have only one atom? Can you guess? The gases of group 18, that is the inert gases. The inert gases have only one atom. So gases like neon, helium, argon, etc. Sorry, Ar. These gases are monatomic and their value is value of gamma for them is 1.33. That will be all for part 1 of thermodynamics. We will continue with the other processes and the other parts of thermodynamics in part 2.